Now let's begin with the delta to y configurations. As well as the pi to t configurations. Okay, perfect. These are the four configurations. This is the delta to y transformation and the pi to t. So we're going to make this claim that these can in fact be related to one another, that these circuits can be equivalently represented using that configuration. Noting that delta and pi are exactly the same. We just represent them differently. So here, this node C is this node here, except we've split it up, as well as y is the same as t. Here you can just see that simply this is not represented at an angle anymore, but at right angles. It's simple configuration. Let's begin to note, how can we relate all four of these combinations? How can we transform from the delta to the y configuration? Let's note that the nodes A, B, and C exist within all four of the configurations, and that is how we are going to begin to relate. So we can say what is the resistance from A to B over the different configurations. So in the delta case, RAB is RB plus RC in parallel, RB plus RA in parallel with RC. So let's note, if we have these two nodes here, we have this resistor, RC, in parallel with the series combination of RB and RA. Let's simplify this equation further. Using the special equation of two resistors in parallel, we have RC multiplied by RA plus RB over RC plus RA plus RB. And let's note that this is in delta. In the y case, this node is left floating. So the resistance RAB is simply the sum of R1 and R2. So RAB in the y case is simply R1 plus R2. Furthermore, let's look at the nodes R, or the resistance between nodes R, B, and C. Again, we see that it's the parallel combination of resistor RA with the series combination RB and RC. So we have the series RC and RB, so we write RB plus RC in parallel with the resistor RA. Again, we can further expand this equation. RA multiplied by RC, RB, RC over the sum of RA, RB, and RC. And yet again, RBC for the y case is simply the sum of resistor 2 and resistor 3. Because we leave this node floating, it does not come into play. Finally, let's look at RCA in the delta case. So this is the resistance seen from node C to A. So again, we have RB in parallel with the series combination of RA and RC. Okay, wonderful. Let's review what we've done here, just to be exactly clear what we've done. So the resistance that we see between nodes A and B, RAB, we stated that it was the parallel combination of RC with RA and RB. If this is not exactly clear, let's write it out. We have RA, such as with node A and B. We have RC here with RA and RB. So here, perhaps it's more clear why it's the parallel combination of resistor RC with the series combination of RA and RB. So we sum these first, and then we do the parallel combination with RC to get RAB. And we do this similarly for each of the resistances between the nodes. Wonderful. Now we're going to do quite a little bit of algebra. Let's say that we wanted to know what R1 was, given that we know what RA, RB, and RC is. How do we get R1 in its own equation? So let's start off. We have R1 is equal to RAB minus R2. This is our first equation. So R1 is equal to RAB minus R2. So we've taken this equation and we've just made R1 the subject of the formula. We do something similar with the second equation, where we make R2 the subject of the formula. So this is RBC minus R3. This is equation 2. Then we have, for the last equation, R3 is the subject of our formula, where we have RCA minus R1. This is equation 3. Then we can use all three of these equations and we sub for each of them R2 into here, R3 into, apologies, that is a mistake, this shouldn't have been RC, it should have been R3. So we take equation 1 and we sub R2 into here, we take equation 2 and we sub R3 into here. So we have R1 is equal to RAB minus RBC plus R3. Then we have, subbing the third equation in, R1 is RAB minus RBC plus RCA minus R1. So what we get then, we use this as our fourth equation. From 4, we can get that 2 of R1. So we take R1, add that to the left side of the equation, is RAB minus RBC plus RCA. Now we know what RAB, RBC, and RCA are. They are RCA, RAB, RCA, RC, RA, RB, RC, RA, RB. It's just these combinations. Let's first note that the denominators in each of these fractions are all the same. So we're going to skip writing out each of these in their own form, and we're going to simply sum all the fractions. So RAB is RC times RA plus RB. So let's multiply out that bracket. So it's RC, RA, RC, RB. Wonderful. So then we have minus RCB, which is RA, RB, RC, the bottom of the fraction, and then RA, RB. So we have minus RA multiplied by RB. And then we have, again, minus RA times RC. Finally, we have RCA, which is RA, RB, RC, the denominator, and then we can add RB times RA plus RB times RC. Perfect. Let's expand this fraction just a little bit. Now we need to identify like terms. So this is RA, RC. We'll find that that is the same here. So we have one here, one there. RB, RC. It exists there and there. And then RA, RB. So third like term. So we see that RA, RC, and RA, RC, our first similar term, cancel one another out. Similarly with RA and RB, over here, our third similar term, they cancel one another out. And then finally, we are left with R2, RB, RC over RA, RB plus RC. And this is equal, long ago, to 2R1. So we can get R1 as RB, RC over RA, RB, and RC. And this can be done for R2 as well as R3. And if we would like to, we could further do RA, RB, and RC. And we can get those in terms of the Y or the T resistors. So let's see what we've done here. We have R1, which is this resistor, in terms of the three resistors in the delta configuration. So what we've created here is essentially a transformation. Given that you have this configuration, this delta configuration, and you have RA, RB, and RC, we can do this transformation. We can utilize these equations to transform these resistors into the same Y configuration. And thus, we conclude that they are essentially equivalent when looking from RA, or looking from the nodes A, B, or C. What we've done today is the current divider and the voltage divider circuits, and we explained the delta configuration and the Y configuration, and we derived the equation for the transformation between these two configurations.